Okay, we're in the flow lab today and we're going to review some of the basic nomenclature of an Exactrix system that's being shipped to Nebraska today. And so we're able to point out here that we're using the Deere GS3, GS2 system for control. And so this is the control panel here that I'm pointing to. And right now it's been dialed in at about 2.1 miles per hour, just creeper speed startup. So that is the control panel up in the cab. And here over to the side of it is the pressure gauges and the tachometer. I'm going to increase the ground speed up to about 7 miles an hour. You can hear the pumps speed up a little bit. And there we are right now at about 7. And you notice how the pump RPMs came up. And so pump 1 is the 2KC, that is the NH3 pump, and pump 2 is the speed of the liquid pump. So in the background you can see the liquid pump running, shaking a little bit, so it's turning about 102 RPM. And on the right side of that is the 2KC, and it's turning 178 RPM. Now this is at 7 miles an hour and we have dialed in a 10-gallon rate on the liquid pump, and we've dialed in a 150-pound in rate on the NH3 pump. Of course, in practice the NH3 pump will be turning about 100 RPM faster to 150 because it has the boost to the tank. So we're running primarily water through the system right now. And also on the gauge panel you'll notice pressures, and 1 and 2 are NH3 and 3 and 4 are liquid. And so those pressures are being read at the final filter and at the BPOR. This one's being read at the terminal injection point, which is a little lower pressure because of line drag, and then this is at the primary filter. So 39 is the injection pressure, 45 is at the primary filter, 41, 42 about the same on the liquid side. So what we want to keep in mind is that these systems are operating at very precision application, and that's because of the way the system is designed. So on the nomenclature side, this is the mass meter of the 2KC, and that mass meter is weighing the material as it's applied. So you get this absolute uniform application because of this sliding vane pump. The sliding vane pump is here. And so on a flow basis it's coming in through the phase shifter, into the sliding vane, around and out the sliding vane, into the mass meter, out past the mass meter, past the discharge valve, and we'll explain the discharge valve a little later. And of course the mass meter is reading the flow, and right now it's reading a flow of about 16 pounds per minute. So once again I want to point out this is a presentation. It's just basically to get the nomenclature down, and we'll explain a little bit more about the details. But just to reiterate, this is the phase shifter. This keeps the ammonia as a liquid going into the sliding vane, out of the sliding vane, past the mass meter, past the discharge valve, and from the discharge valve the flow goes up here to the liquid manifolds up here, and that maintains the ammonia as a liquid. Then those lines circulate on out, they go to the injection point, and there's a terminal orifice at the injection point. From the manifold that you see up here, the lines travel on out into this opener and into the injection point, and you can see that there are orifices there that hold the back pressure up and allow the injection of the ammonia and the polyphosphate as a liquid. So once again, taking it from the inlet clear to the outlet, And these orifices allow the ammonia to be directed into the soil where you want it to go, along with the polyphosphate, and then it's injected in a liquid state so you get a nice even lineal band. So once again, orifices are very key in the injection. Here's another view of an orifice group that has been utilized in the system, and you can see the two lines coming together, and they're actually, if you get a side view, they're trying to collide and mix the material to make triammonium polyphosphate sulfate. So it takes two pumps, two systems. It takes a liquid system and an ammonia system with high pressure to perform this chemical process. It's a physical process because the application is made at 1% CV, and it's a chemical process because we're able to combine the two materials. Okay, so that's kind of like half of the story, and now we're going to go over and do the nomenclature of the liquid system. Okay, this is the liquid part of the TAPS formulator, and we use a 3-cylinder pump to build pressure and to get flow, and this pump is designed from poly materials, so you can use very difficult materials such as KCl or materials that have some chloride in them can be utilized with this pump design. So this is the pump, the hydraulic motor. There's a tachometer circuit here. The flow is coming out of the pump past this bypass valve. You see the bypass valve, a little pressure gauge there. Comes around and through this flow meter. This is an Airig flow meter. On out past the flow meter, and it goes into the manifolds and injects into the ground, as we showed previously, the two orifices coming together. So these are both these pumps are running off of the controller, and the producer can select or split his screen to show what's going on with the systems. And then we use the pressure gauge and the tachometers to double check the system to make sure it's applying correctly. Well, that's kind of the nomenclature discussion today. It takes 3 critical parts to make a good Exactrix system. It takes a PD pump that gets the pressure up, provides us tachometry. It takes a dual staging manifold, high quality manifold to get that 1% CV. It takes that terminal orifice to get the delivery right down to 1% coefficient of variation across the board. Thank you.